Originally we have exact states, and then we exact states, and then we expand the exact states in a basis of many electron wave functions, and essentially it's the same basis we always use. It's going to be Slater determinants. And then the question comes up again, which kind of Slater determinants do we include? We have single excited, double excited, triple excited, quadruple excited, and so forth. And how do we describe the ground state? And we have to describe the ground state and the excited state in some way. And different methods use different representations for those. And what I want to give you, so that's the last thing, is a short summary of what kind of methods we have around. Now, one thing is what is our reference status and what kind of excitations we allow in order to get the excited states. So, different response theory methods, and I think I need a bit more space. So we have, one is, what is the reference state? So how do we describe the, our unperturbed reference state? And then is, what kinds of excitation we include in order to describe the excited states, in order to expand basically the N. And obviously the lowest level is we just use Hartree-Fock. And then we describe the excited states by single excitations. Single excitations. S. So we have single excited states. And this kind of response theory has many names. You could call that an SCF or Hartree-Fock linear response function. It is also called time-dependent Hartree-Fock, because of time-dependent perturbation theory doing with Hartree-Fock, you get time-dependent Hartree-Fock. So this would be that, that would be SCF, linear response. That would be another acronym. It has a very strange acronym, which is RPA, called the random phase approximation, which goes back to the fact that physicists have invented that a long time before chemists started to use that. That's the random phase approximation. And for the static case, there are even more approximations, more names. You can call it coupled Hartree-Fock or coupled perturbed Hartree-Fock if it's for the static case for frequency equal to 0. You can use, obviously, if you can use a Hartree-Fock, you can also use a CompChem determinant and single excitations, and that is time-dependent DFT. Which is basically, as always, the same as Hartree-Fock. The only difference is that instead of the Coulomb and exchange integrals, you have the color integrals and whatever functional you use, whatever integrals you get from the exchange correlation functional. But otherwise it's all the same again. Obviously you can use some Möller-Blessed nth order perturbation theory wave function. And you can use single, double, triple, and so forth excitations to get the excite states. If you do that with an MP second order, up to second order, and you do single and doubles, you get the method which you already used before, which is called SOPR, which is a second order polarization propagator approximation. And that is sort of going from Hartree-Fock to Möller-Blessed. You can use an MCSTF state. You can use then single excitations and something which is called state transfer operators. That is operators which brings you from one of the configurations which you have in the MCSTF to another configuration. So state transfer operators, and that you can call that multi-configurational, time-dependent, Hartree-Fock, or whatever you want to call it, MCSTF linear response. You could also call it multi-configurational RPA. It's all the same. And then you can use whatever coupled cluster method you're fond of. And then you're going to have here, if that sort of coupled cluster method XY, then you're going to have X and Y excitations also here. And that is then coupled cluster XY linear response. So essentially, the operators which you have here to generate the excitations are very much the same operators which you have here in order to describe the ground state wave function. In Hartree-Fock, you have what is called these orbital rotations. That's single excitations. In Möller-Blessed, you have single, double, triples, whatever. Here you have single doubles, so in the SOPR you have single doubles, MCSTF and coupled cluster. If it's CCSD, you have single and doubles. If it's CCSDT, you have single doubles and triples. If you have CC3 or CC2, you have the same kind of excitation and the same kind of approximations to your E and S matrix as you had when you found the amplitude equations. In all these methods, you can get the excitation energies by finding the singularities, meaning solving the generalized eigenvalue equation which belongs to this. There are slight differences between the different methods. STF, SOPR, MCSTF, it's a nice symmetric eigenvalue problem. Coupled cluster, it's an asymmetric eigenvalue problem, but in general it's the same procedure. And if you want to have a property, a frequency-dependent polarizability for a given frequency, you have to calculate the whole thing. You have to, in principle, you would have to calculate the inverse of that matrix. And the dimension of the matrix depends on what kind of operators you have. Hartree-Fock and DFT, that has the dimension of all possible single excitations in your one-relation basis set. CCSD, single and double excitations. CCSDT, single, double, triples excitation, and so forth.